So when you hear the word matrix, you may think of a lot of different things, but it is just a rectangular array of numbers. Each number in the matrix is called an element or an entry. And so they give this example right here. This is a matrix. Couple things that you want to know about matrices. They are named with capital letters. Inside the matrix, we're going to have some lowercase variables, but matrices are always labeled with capital letters. The elements are arranged in rows and columns. So your rows run this direction, right? These are your rows. Your columns, just think of like a column on a house, they run up and down vertically. Okay, that's important because when we start doing matrix multiplication, how you arrange them is important. Dimensions, they do have dimensions. The dimensions of the matrix are listed with a little X, like you would think of dimensions of anything if you've ever had dimensions of a room or anything like that. M represents the number of rows and N is the number of columns. So when you list the dimensions, you would list rows first and then columns. So for this particular one, you would say that M is a 2 by 3 matrix, all right? And then some notation for that, you can see that you have the capital letter M and a little 2 by 3 underneath it. That just tells you the dimensions of that particular matrix. Matrix also, when you're just listing the elements, you have brackets here. The brackets are closed, open brackets where they almost look like absolute value signs without that little clip at the top of the bottom. That actually means something else for matrices. And so when you're writing out a matrix, you have the little dash at the top of the bottom to indicate you're just giving me the elements, all right? So let's look at some of the things you do with them as far as just recognizing the different pieces of it. This says state the dimensions of each matrix. So if I were to state the dimensions, I would say my rows and then my columns. So this would be a 2 by 2. So the dimensions here would be 2 by 2. If I looked at this, I have 1, 2, 3, 4 rows and 3 columns. So 4 by 3. This is a special type of matrix. This actually only has 1 row and 4 columns, and this is called a row matrix. So when you have just 1 row, it is a row matrix. This one actually is a 3, so 3 rows and 1 column, and so this is called a column matrix. By the way, this guy is called a square matrix. I don't think they define that right now. Oh yeah, they do. A square matrix. Anytime your dimensions are the same, it's a square matrix. That makes sense, right? Because dimensions of a square are the same. So you have some special cases here. A, C, and D are all special types of matrices. All right, let's look at the elements. Look at example 2. So each element is named. This is not 11, 12, 13. It looks like it, but this is actually telling you where you are. So this is telling you the row, and this is telling you the column that you're in. And so if it asks for a specific element, it's going to list that. It's going to say, I want this specific element. And it's actually telling you to go to that row and column that it's telling you to go to and give back the element that's in it. So if you look at the top, page 147, it says state the value of each element. This right here is asking for row 1, column 1. And so if I were to give that element, I would go to row 1, column 1, and I would see that element is 3. This one here, row 2, column 3. So I'm going to go to row 2, third column, and I'm going to get a 14. And so that's how all of these would do. Row 4, column 4. That's going to give me the 8. Row 3, column 1. That's going to give me a 12. All right. And so how this is actually used sometimes in word problems. Very often they like to use it in standardized tests as well. But one of the key things you'll see is they love bar charts, right? They love interpreting these. And so very often they will interpret a bar chart with a matrix because then they'll do something else with it to quickly find information. And so you can see that they listed their rows as the months. So we have January and February. Those are the months. They've color coded them. January's are the blues. February's are the reds. And so those are my rows. And then my columns are my weeks. Week 1, week 2, week 3, week 4. And so we have our week 1, week 2, week 3, week 4, right? And that's the actual bar graph piece of it. And so then they just said, well, in week 1 in January, what did I have? Well, I had 5. In week 1 in February, what did I have? Well, I had 6. And so they've just listed this with the different weeks that match up to this bar chart. And so then what happens with a bar chart, that's fine. But then when you put it in a matrix, you can very quickly see either a trend or something like that, or very quickly pull an element that you need. And then sometimes you actually, we're going to get to multiplication. You can then multiply it by something to quickly get information on what happens if all of these are multiplied by something. And so very often they'll convert one to the other, either bar chart to a matrix or vice versa. All right, let's try some of these. They've given us this matrix here. They want us to state dimensions, number of elements, list these elements, actually list the label for these elements and list the elements that go with those labels. Matrices can represent data. They can also represent figures on a coordinate plane, all right? And so when you have figures on a coordinate plane, which I think we did a little bit of this in geometry, your first row represents your x coordinates and your second row represents your y coordinates. So you can actually plot them based on what they've given you. And so A is actually the point 0, 0. You just read it down. And so if I wanted to plot that point, I would go to 0, 0. That would be my A. The next one would be 2, 3. So 2, 3 would be my B coordinate. 5, 2 would be my C coordinate. 4, negative 3, D. And then 3, 1 would be E. All right. And so then you just actually go in order that they've given it to you if you want to see what figure you have. So for this one, you're going to go from A to B, right? And then from B to C, just like you would if you were doing connect the dots, right? And so that would be your figure on a coordinate plane, all right? And this is what we did in geometry where we translated them, where we slid them around the graphs and reflected them and rotated them using matrices. You can do that with a matrix as well. All right. Equal matrices have the same dimensions and have equal corresponding elements. Those elements in the same relative position. So if you have two matrices that are equal, then every single piece of the matrix is also equal, meaning every element that corresponds to the element in the other matrix is equal. This is one of the ways that you're going to solve equations with matrices, is something like this. They have told us that this matrix is equal to this matrix, which means each corresponding element, 1, 1, 1, 2, just if you were to follow those columns and rows across, then you could figure out what all the small variables within them represent. And so like for this one, I have this is in row 1, column 1, which means these two are equal. So A equals 7. 2B would be equal to negative 8. 3 would be equal to C minus 5. And 3D would be equal to D plus 6. All right. And so if they wanted me to find the values of these variables that are in there, you're literally just solving. A was given to us. B, we're going to divide both sides by 2. C, we are going to add 5. And D, we're going to subtract that 1D over and then divide by 2. And you should see that D equals 3. And so if you know they're equal, you can do your properties of equality and just solve very simple equations on the inside. that represent those variables. All right, matrix addition and subtraction. Matrix addition and subtraction. So now we're talking about the entire matrix. If you're solving elements within it, then you're just using basic algebra equation solving. You can actually add or subtract the entire matrix, all right? To add or subtract matrices with the same dimensions, add or subtract their corresponding elements. In order for you to be able to add or subtract a matrix, they have to have the same dimensions. If they don't have the same dimensions, then when you go to add or subtract, there will be an element missing and you won't be able to do it. And so the first thing you have to establish is, can I add or subtract these? So the first thing you want to figure out is your dimensions. My dimensions of A, well, that's a 2 by 3. My dimensions of B, that's a 2 by 3. That automatically tells me I can add or subtract them. All right. And then your same properties apply, which we're going to look at. If they want me to add A and B, then that means they want me to take the entire matrix here, the entire matrix A and the entire matrix B, and add the corresponding elements. All right. Very simple. I'm going to say 2 plus 4, and my answer here is going to be another matrix by the same dimensions. 2 plus 4 is 6. 7 plus 2 is 9. 0 plus -1 is -1, and that's my first row. And then 3 plus 1 is 4. 1 plus -2, -1, and 5 plus 3 is 8. Very, very simple, right? And then the same is true if I wanted to subtract. If I wanted to subtract these, then I would just take those and I would do subtraction. And so I would say the same two matrices, and I would subtract the elements. The only thing I would say to watch with subtraction is your positives and negatives, because remember, you are subtracting across, not adding. So we have 2 minus 4. The biggest problem I see here is people getting our negatives wrong. This is 0 minus a -1. Minus a -1. So it's like +1, right? And then the rest of them, obviously, 3 minus 1, that's going to be 2. But then we have 1 minus a -2. So that's 1 plus 2, right? So just watch your positives and negatives when you're subtracting. Most of the time people are okay with adding, but when you're subtracting, you are subtracting a negative sometimes. And so make sure you pay attention to your rules there. But other than that, adding and subtracting is pretty straightforward. I want to talk about the additive inverse just because it's going to come into play when we start solving equations. But just like in regular addition, additive inverse or additive identity really is part of the properties that allow you to do the addition and subtraction across the equal sign. And so in matrices, if you add zeros, like if an entire matrix is 0, that's the additive identity. Because if you add all zeros to a matrix, none of the elements are going to change, right? The identity doesn't change. Additive inverse, if you were to add the opposite of all of your numbers, then it would zero it out. And so just like in regular solving of equations, you can actually add or subtract an entire matrix across the equal sign to solve for another matrix, all right? And the same rules apply. Whatever you add to one side, you add to the other. Adding the inverse will zero it out. It doesn't matter what order you add it in because you're just adding two numbers within it, so order doesn't matter. It doesn't matter for grouping if it's all addition. And closure, if you add, you have to have the same dimensions, and so your answer will be the dimensions that you started with when you add matrices. And so we use this when we're solving equations. We have one more thing that we do with matrices that we do with regular numbers, and it's multiplication, okay? And so there are two types of multiplication. The one we're going to talk about today is called scalar multiplication. The reason it's called scalar is because you are taking the matrix and you are increasing every single element by the same scale factor, okay? This is exactly what's used when you blow up a picture, right? If you make it 150%, then you are multiplying every piece of that picture by the 1.5. If you don't multiply all pieces, your picture is going to be skewed. And so for scalar multiplication, you are literally taking every piece of the element, every element, and multiplying by it a scale. And so it will look just like this. They will have a scale factor in front of it multiplied by a specific matrix. And they want you to take this matrix and multiply everything by this number. It's like a coefficient, but for a matrix, all right? And so if I were to do this first one, 1/2 A, I'm going to multiply every element in here by 1/2. I will have a 2 by 2 matrix when I'm done. 4 times 1/2 is 2. 0 times 1/2 is 0. 2 times 1/2 is 1. 5 times 1/2 is 5/2, right? This is true for all of these. If I were to take B and multiply everything, I would take everything and multiply by -5. And then you can get a combination of them. You are going to use order of operations, just like you would. Meaning, I will do my scalar multiplication first, then I will do my addition subtraction second. And so if I were to do this, I would take my 3 times my A first, and then I would take my 2 times my B, and then I would do my subtraction here, okay? And so you would just now subtract across, right? And so 12 minus 4, 0 minus 8, 6 minus 2, 15 minus 6, right? And then this would be my answer to do that scalar and that subtraction, all right? All right, so you can solve equations. You'll notice the difference between this and the first one we did is it is a capital letter X, right? So when you see that capital letter, your answer is going to be a matrix, all right? It's not going to be one number like it was for the first example. You're not solving for an element within it. You are solving for an entire matrix as your answer. But you are really going to do this exactly the way you would solve. If I had some number minus 2x equals some number, I would just solve for x, okay? And so you're going to do that by subtracting your matrix over, dividing every element by -2. So it is the same exact process. You're just moving an entire matrix at this point. And so I am going to follow the same rules that I would if I were solving an equation. I would take the matrix and I would subtract the entire thing from both sides, right? And so I'd subtract it from this side and then subtract it from the other side. And just like in regular algebra here, it cancels. That's what we talked about. If you subtract it, the inverse cancels each other, just like if that were a 5 and I subtracted a 5. Because I am taking each element, 2 minus 2, 0, 1 minus 1, 0, 3 minus 3. I'm subtracting each one of these. This whole thing zeroes out, right? And so that's my first step. I do have a -2x left. So I would have -2 x as in a matrix x, and then I would just subtract these. And so on the right side here, I am going to have a matrix, 3 minus 2, 5 minus 1, 2 minus 3, 1 minus 3, 4 minus 5, 1 minus 1. And then I'm going to do exactly what you would think. So if you can scalar multiply by -1/2 is the same thing as dividing everything by -2 on the other side. And so if I'm dividing everything by -2, that's like multiplying everything by -1/2, which I can do. It's scalar. So my matrix is going to look like this. I have 1 divided by -2, 4 divided by -2, -1 divided by -2, -2 divided by -2, -1 divided by -2, and 0 divided by anything, right? And so that would be my answer to what the matrix X would be. And just like algebra, you could plug it back in and solve. You could plug it back here, multiply everything by -2, subtract it from this, and you would get your answer. And so you're doing exactly what you would do in regular algebra, solving for the variable that you are looking for, Move everything that's not with a variable first, divide or multiply depending on what you're doing, and then you'll solve for your variable. It's just a multi-step operation here.